Hello and welcome. In the previous lesson, we learned about the linker script. It instructs the linker program how to place the different memory sections from the input object files in that of the output files. In this lesson, we shall learn how to define C functions for interrupt vector table, reset, ISR, and other important functionalities. The C functions for interrupt vector table and reset ISR are defined in the interrupt.c source file. The interrupt vector table is placed in the function named __vector_ table. It is implemented as a C function with inline assembly instructions. The function neither accepts any argument nor return any value. The first instruction is a jump instruction to the memory address where the reset ISR is placed. Then the jump instruction for the external interrupt 0 follows. Then external interrupt 1 and so on and so forth. Notice the jump instructions are placed in the exact same order as the interrupt vector table discussed earlier. The sequence of these jump instructions is very important and must not be changed. The function defining the interrupt vector table seems to be a usual C function. How is the linker informed that it must be placed at the memory address 00? The function prototype of the function __vector_table defines two attributes. Those are naked and section as shown. The attribute naked instructs the compiler not to add the prologue and epilogue to the function and allows the body of the function to be assembly code. The attribute section allows the programmer to place the code in the section specified, which is .init0 in our case. Notice that other functions like __reset_ISR, __do_copy, and others are placed in the .init0 section. But with the sequence of the function prototypes, the __vector_ table is always placed at the beginning of the .init0 section, and the section .init0 is the first section in the .text section. So, the jump instructions in the function __vector_ table is always placed at the beginning of the program memory. In the interrupt vector table, the ISR is defined for reset and external interrupt 0. For others, the jump instruction points to the __undef_ISR. It is a function defined in interrupt.c source file and acts as a placeholder for interrupts whose ISR is not defined by the programmer. The function contains a jump instruction to branch the program execution to the start of the vector table. So, occurrence of such interrupts effectively resets the microcontroller. We shall discuss how to define ISR in subsequent lesson. The reset ISR follows the interrupt vector table. It is defined as a C function with inline assembly code. The function prototype is defined with attributes naked and section. The reset ISR does three things. 1. It initializes the register R1 to 0 with XOR instruction. 2. It initializes the stack pointer to the highest memory address of the SRAM. For the Atmega 328 microcontroller, it is 08FF. The register pair R29 and R28 is loaded with the value and the stack pointer high and low bytes, that is, the addresses 3E and 3F, are initialized using the value in the register pair. 3. It enables interrupts using SEI instruction. Notice the reset ISR does not have return instruction. That means when reset occurs, the program execution continues on to the subroutine defined after the reset ISR. The functions underscore underscore do underscore copy and underscore underscore do underscore clear underscore BSS follows the reset ISR in the sequence. But what is the need of these functions? Remember, we discussed about the global variables in the earlier section. Global variables are stored in the heap memory. Heap memory is a part of SRAM where global variables are stored during the program execution. Effectively, it is the portion of the SRAM that is not used for program stack. But when the program is compiled and flashed, the global variable is in the program memory. The part of the memory containing the global variables must be copied to the read-write memory, that is SRAM, before program execution starts. The .data and .bss sections contain the initialized and uninitialized global variables respectively. The function underscore underscore do underscore copy copies the content of .data section from the program memory to SRAM. And the function underscore underscore do underscore clear underscore BSS initializes the memory locations in SRAM with 0 for uninitialized global variables. Do you remember that we have defined a few symbols in the linker script? These symbols are used in these functions to know the start and end addresses of the .data and the .bss sections. The linker script defines the symbol underscore underscore data underscore start underscore underscore data underscore end underscore underscore data underscore load underscore start and underscore underscore data underscore load underscore end for the .data section, and the symbols underscore underscore bss underscore start and underscore underscore bss underscore end for the .bss section. The symbols, as name suggests, are the start and the end address of the sections. In the function underscore underscore do underscore copy, the register Z is loaded with the address underscore underscore data underscore load underscore start, and the register X is loaded with the address underscore underscore data underscore start. Then the instruction LPM, that is load program memory, copies the content of the address pointed by the register Z from the program memory to register R0. The instruction ST, that is store indirect, stores the content of the register R0 to the address pointed by the register X in the data memory. This continues until the entire content of the .data section is loaded into the data memory. Then the program execution jumps to execute the instructions in function underscore underscore do underscore clear underscore BSS. In the function underscore underscore do underscore clear underscore BSS, the register X is loaded with the address underscore underscore BSS underscore start, and the register R17 is loaded with the high byte of underscore underscore BSS underscore end. The addresses in the data memory pointed by the address in the register X is stored with the content of register R1, and we know the register R1 contains 0 as initialized in the reset ISR. This continues until the entire memory in .bss section is initialized. Then the program execution branches to execute the instructions in the function main. This is achieved by instruction jump main. Once the program execution returns, it jumps to execute the function underscore underscore exit. The function underscore underscore exit disables the interrupts using the CLI instruction, and the program execution is trapped in an infinite loop. Notice that All the functions discussed have prototypes defined with the attributes naked and section. The functions __vector_table, __reset ISR, __do_copy, and __do_clear BSS are placed in the .init0 section, but the __exit is placed in the .finit0 section. The .init0 section is the first part of the .text section and .finit0 is the last part of the .text section. The rest of the .text section from all the input files are sandwiched between these two sections. Thus, the interrupt vector table, reset ISR, and the initialization of .data and .bss sections are placed in the program memory with the help of linker script and defining these functions in a certain way. With this, I conclude the lesson. In the next lesson, we shall learn about implementing the interrupt service routines. Until then, have fun learning.